let's learn about compounds of alkali metals. Here, let's first take up oxides of alkali metals. You know, oxides are binary compounds of any element with oxygen. We know very well that alkali metals can give rise to three types of oxides. We have seen in the previous discussion that when alkali metal reacts with oxygen, you can get three different types of oxides. We said normal oxide, peroxide and superoxide. So, oxides of alkali metals may be classified into three types: normal oxide, peroxides and superoxides. Alkali metals can give rise to three different types of oxides when they react with oxygen: normal oxide, peroxide and superoxide. The general representation of a normal oxide is M2O, general representation of peroxide is M2O2 and the general representation for superoxide is MO2. Let's make a comparison of these three types of oxides. Here M stands for alkali metal. One important point regarding this is lithium superoxide does not exist. Lithium does not form superoxide. Here we blame the small, very small size of Li+. Due to its extremely small size, lithium does not form superoxide. It is so small that it cannot stabilize a very large superoxide ion. Lithium does not form superoxide. LiO2 does not exist. In all these compounds, oxidation state of alkali metal is +1 only, but the oxidation state of oxygen is different in different types of oxides. Here the oxidation state of oxygen is -2. In case of peroxides, it is -1, and in superoxides, oxidation state of oxygen is -half. You can as well put it like this: in all the compounds where oxidation state of oxygen is -half, they can be regarded as superoxides. In compounds where oxidation state of oxygen is -1, you can take them as peroxides, and those where oxidation state of oxygen is -2 are simply called as normal oxides. So, peroxides, oxidation state of oxygen is -1, superoxides, oxidation state of oxygen is -half, and normal oxides where oxidation state of oxygen is -2. Now, remember, regarding stability of superoxides, remember stability of superoxides increases down the group. It is because of increase in the size of cation. A large cation, can efficiently stabilize a large anion. Superoxide anion is a large anion, and to stabilize it, you require a large cation. Cesium ion is the largest among alkali metal cations, so cesium is best able to stabilize superoxide ion. So, when you compare superoxide stability, the most stable among them is cesium superoxide, and the least stable is sodium superoxide. I am not mentioning lithium superoxide because we already said that lithium does not form superoxides because of its extremely small size. Same stability order is possible also for peroxides. Peroxides also follow the same order of stability. It is not that very significant, but what is more important is order of stability of superoxides. There are some more points regarding these compounds I am going to give you. Just remember, before I erase this, remember that there are three types of oxides formed by alkali metals: normal oxides of the formula M2O, where oxidation state of oxygen is -2; peroxides, where the general formula is M2O2 and the oxidation state of oxygen is -1; then superoxides, whose general formula is MO2 and oxidation state of oxygen is -half over here. Lithium is the only alkali metal which does not form superoxide. Lithium can form normal oxide and peroxide. Two types of oxides of lithium are possible: normal and peroxide, whereas for all other alkali metals, three types of oxides are possible: normal oxide, peroxide and superoxide. The order of stability of superoxides increases down the group due to increase in the size of cation, because a large cation can efficiently stabilize a large anion. Let's move on to the further discussion of about oxides of these elements. Remember that normal and peroxides are colorless and diamagnetic. Normal oxides and peroxides of alkali metals are colorless as well as diamagnetic, whereas superoxides are colored. They are generally yellow colored and they are paramagnetic. This is one very important point you are supposed to know, that superoxides are colored as well as paramagnetic. Normal oxides and peroxides are colorless as well as they are diamagnetic. See, if you find any peroxide colored, just remember that it must be, the color must be due to some contamination of superoxide. Pure peroxide is expected to be colorless. Pure normal oxide is also expected to be colorless as well as diamagnetic. Now, another important feature, see, the reaction with water. If a normal oxide is dissolved in water, it gives rise to metal hydroxide. So, a solution of normal oxide will be alkaline. It is because of formation of metal hydroxide. When a peroxide is dissolved in water, you get, here also you get metal hydroxide. Apart from this, you also get hydrogen peroxide. Peroxides dissolve in water to give alkaline hydroxide, and hydrogen peroxide is also formed in this reaction. Superoxides, when dissolved in water, let's see how superoxides react with water. Superoxides, when dissolved in water, here also you get alkaline solution due to formation of metal hydroxide. You get hydrogen peroxide and oxygen gas is produced. This is how they differ in their reaction with water. Normal oxides give metal hydroxide, peroxides give metal hydroxide solution, and hydrogen peroxide is formed. So, I can put it like this: peroxides dissolve in water to give alkaline hydrogen peroxide. This is generally used as a oxidizing agent. Superoxides dissolve in water and they also give alkaline hydrogen peroxide. Apart from this, oxygen gas is also produced in the reaction. This is how they react. Now, please go through the reactions once. In all the cases, metal hydroxide is formed. In case of peroxides, you get hydrogen peroxide. Even in case of superoxides, you get hydrogen peroxide. And what is special regarding superoxides? It's superoxides also produce oxygen gas. Let's proceed further regarding oxides of alkali metals. Look at this important reaction of superoxide. Now, look at this important reaction of superoxide. When a superoxide reacts with carbon dioxide, what you get is metal carbonate and oxygen gas. This is a very, very important reaction. You try to realize the significance of this reaction. In this reaction, carbon dioxide is absorbed and an equivalent amount of oxygen gas is produced. So, a superoxide can absorb carbon dioxide and can produce equivalent amount of oxygen. This feature is very, very, very important in space capsules, in tube railways. It is a very important feature. It is also useful in crowded places where there are a lot of people breathing in oxygen and giving out carbon dioxide. This is giving out oxygen and taking in carbon dioxide. That is the significance of this reaction. So, alkali metal superoxides are used for increasing the quality of air. This use is in space capsules. They can be used in submarines. They can be used in tube railways to avoid suffocation due to increase in the concentration of carbon dioxide. That completes oxides of alkali metals. Let's move on to another class of compounds of alkali metals. Now, before I go to another class of compounds of alkali metals, I want to ask you one question. See, if you are given different superoxides of alkali metals and asked which of these is expected to be most stable, you'll have to select the one with largest size, isn't it? Imagine the options are sodium superoxide, potassium superoxide, rubidium and cesium superoxide. Then the correct answer, the thermally most stable among them, is obviously cesium superoxide. Then if different types of oxides of alkali metals are given and you are asked which of these is expected to be colored, and then you will have to select not normal oxide or peroxide, select superoxide. Superoxides have a general formula MO2. And then a similar question may be asked like which of these compounds is expected to be paramagnetic. Again, remember that superoxides are paramagnetic. Now let's move on to the next class of compounds of alkali metals, that is hydroxides. See, the general formula for hydroxides of alkali metals is MOH. Alkali metals form MOH type of hydroxides. Now, in order to prepare this hydroxide, we have already seen that the metal hydroxide can be prepared from metal as such. If you react it with water, you can get metal hydroxide. There are, of course, other methods of preparation. We'll learn preparation of sodium hydroxide in the separate section in the next topic. Now, let's talk about some properties of hydroxides. Remember that all are strong bases except LiOH. See, among hydroxides of alkali metals, the weak base among them is lithium hydroxide. All others can be termed as strong bases. Sodium hydroxide, potassium hydroxide, rubidium and cesium hydroxide. All these 4 hydroxides are strong bases. Lithium hydroxide is a weak base, weakest base. And another important point regarding these hydroxides is all are thermally stable except LiOH. All are thermally stable except LiOH. That means if LiOH is heated, if you heat lithium hydroxide, it will decompose to give lithium oxide and water. On heating, it will decompose to give oxide. Now, here I would like to emphasize on this. What is thermal stability? See, if a compound on heating decomposes, it is said to be unstable thermally. But if it melts on heating, if it is a solid under ordinary conditions, and on heating, if it melts without decomposition, then it is said to be thermally stable. For your information, remember, among all the metal hydroxides, alkali metal hydroxides are thermally stable. Others are thermally unstable. They decompose into their oxides when heated. So sodium hydroxide on heating will not decompose, it will melt. Same is the case with potassium hydroxide, rubidium hydroxide as well as cesium hydroxide. So among alkali metal hydroxides, the only one which is thermally unstable is lithium hydroxide. What happens when it is heated? It decomposes to give oxide. Among alkali metal hydroxides, which is the weak base? The answer is lithium hydroxide. So there are 2 exceptional features of lithium hydroxide. It is a weak base and it is thermally unstable. Other hydroxides are all strong bases and they are thermally stable. When heated, they can melt. That's about hydroxides. And there's another important feature I would like to add here. All the alkali metal hydroxides are deliquescent solids. What do you mean by deliquescence? These substances have an ability to absorb moisture from the air. They dissolve in that moisture and form a saturated solution. if a solid substance absorbs moisture, dissolves in it to form a saturated solution, then this substance is said to be deliquescent. So sodium hydroxide is a deliquescent substance. When you keep it exposed to air, it absorbs moisture of air and it dissolves in the same moisture and forms a saturated solution. So this is a property which is common for all alkali metal hydroxides. That's all regarding hydroxides of alkali metals. The next class of compounds of alkali metals we are going to discuss now are halides of alkali metals. Halides are binary compounds of alkali metals with halogen. Here M stands for alkali metal. It can be lithium, sodium, potassium, rubidium or cesium, and X is halogen. X can be fluorine, chlorine, bromine or iodine. This is the general formula of alkali metal halide. I'll tell you once again. X can be fluorine, chlorine, bromine or iodine. You know, we have just seen that these compounds can be prepared directly by combining alkali metal with halogen. This is a balanced equation. So you get MX type of halide. Now remember that all are predominantly ionic. All are predominantly ionic except LiCl, LiBr and Lii. I am not including fluorine because remember, all metal fluorides by default take them as ionic only. All metal fluorides, whatever may be the metal, all metal fluorides are predominantly ionic. Whereas here lithium chloride, lithium bromide and lithium iodide are predominantly covalent, and here we don't blame halogen, actually we blame lithium. Lithium Li plus ion, due to its very small size, has a very high polarizing power. Due to high polarizing power of Li plus, these substances become predominantly covalent. The consequence is remember, lithium halides are, I can say, lithium halides are deliquescent. And exist as hydrates. You can have LiCl dot 2H2O or LiCl dot 3H2O. So all other alkali metal halides are not deliquescent. They do not form hydrates. Lithium halides, they form hydrates and they are deliquescent substances. It is because of their predominant covalent nature. This predominant covalent nature is in turn due to very high polarizing power of Li plus. Another point you need to know is all have FCC crystal structure. All have FCC crystal structure. FCC stands for face-centered cubic lattice structure. FCC, face-centered cubic lattice structure. All the alkali metal halides have FCC structure. Exception is cesium halides. Cesium halides, CSX, are BCC. Cesium halides have body-centered cubic lattice structure. Cesium halides have body-centered cubic lattice structure. All other alkali metal halides have face-centered cubic lattice structure. I want to give you some more information regarding this. For the time being, just go through this. Alkali metal reacts with halogen to give MX type of halide. These halides are predominantly ionic. Lithium halides, especially lithium chloride, bromide and iodide, are predominantly covalent due to high polarizing power of Li plus. Lithium halides are deliquescent and they exist as hydrates. Regarding crystal structure, remember, all alkali metal halides have FCC structure, face-centered cubic lattice structure, whereas cesium halides have body-centered cubic lattice structure. Little more information regarding halides. Come back to this reaction once again. For this reaction, the standard enthalpy of formation is negative. That means this reaction, formation of metal halide, is exothermic. It takes place with evolution of heat energy. One important feature regarding this reaction, regarding standard enthalpy of formation of metal halide, I would like to emphasize is this: the delta H of fluorides becomes less negative down the group. This is a very, very important point. That means the delta H negative value, delta H value is most negative. That means highest in magnitude in case of lithium fluoride formation, and in case of cesium fluoride formation it is least negative. So the reaction will be more exothermic when the metal involved is lithium, and it will be less exothermic when the metal involved is cesium. This is a statement pertaining to fluorides only. In case of fluorides, formation of metal fluoride, that means every time keep X2 as fluorine F2 and then keep on changing this: lithium, sodium, potassium, rubidium, and then cesium. So as you go down the group, delta H becomes less negative. That means more amount of energy is produced when the metal involved is lithium. Reverse is true for chlorides, bromides, and iodides. In case of chlorides, bromides, and iodides, as you go down the group from lithium to cesium, delta H becomes more negative. For a given alkali metal, delta H becomes less negative from F to I. Try to understand these 3 points. Delta H of fluorides becomes less negative down the group. That means as you go down the group in alkali metals from lithium to cesium, on reaction with fluorine, the amount of energy produced, the amount of heat produced will be maximum in case of lithium and minimum in case of cesium. Whereas the order is reverted in case of chlorides, bromides, and iodides. Now, if you take a particular metal, say lithium, and go on changing this from fluorine, chlorine, bromine, and iodine, maximum amount of heat is produced when the halogen is fluorine and minimum when it is iodine. So this is what you are supposed to know about halides of alkali metals. All alkali metal halides have face-centered cubic lattice structure. Cesium halides have body-centered cubic lattice structure. The reaction is exothermic in all the cases, but the heat produced not only depends upon the nature of alkali metal, it also depends upon the nature of halogen. I would like to add one more point here regarding solubility. All the halides are soluble except LiF. LiF, lithium fluoride, is insoluble in water, and we blame high lattice energy of LiF. High lattice energy of LiF is in turn due to its small size of Li plus and very small size of F minus. Cesium iodide also has very low solubility. The reason is very low heat of hydration of Cs plus and very low heat of hydration of I minus due to their large sizes. So that's about solubility. I repeat once again, all are soluble. Lithium fluoride is insoluble. The reason is high lattice energy. Cesium iodide solubility is low due to low heat of hydration of both Cs plus and I minus. That's all about halides of alkali metals.